Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the lecture 7 of the Linux lecture series. Today we are going to talk about the processes in Linux. So before I start with the processes, let us briefly touch about the idea of how a program is converted into a process. This is a brief overview of the compilation process. As you all must be knowing that generally the C compilation process is composed of four different phases. In the first phase, the preprocessor phase, we give the preprocessor the source program and it performs three tasks on it. Include the header files, expand the macros if there are, and remove the comments, and generates a modified source program with the extension of .i, hello.i. We can use this command gcc-e to just pre-process a source file. This will output the code on the screen, and if we want to write it inside a file, we can do IO redirection. By doing something like this. Soon I will repeat these on the shell for better understanding. The next phase is the compiler phase. The compiler is given the pre-processed file and it generates the assembly program. The compiler performs two tasks. The first is it checks for syntax error. Any error inside the source program is checked over here. If there are no syntax error, then the main task of the compiler is that it converts the source to the assembly of the underlying processor. If the underlying processor is x86, which is in most of the cases, it generates the assembly for x86. And if the underlying processor is Spark or Motorola or PowerPC or MIPS or whatever processor, it generates the assembly of that particular processor with the extension of hello.s. If you just want to perform the compilation process, you can use the -s option to GCC and give it the hello.i file. The third phase is the assembler phase. During the assembler phase, the assembly file is given to the assembler and it generates a relocatable object program. Gentlemen, relocation is the process of assigning addresses to different parts of the program by merging all sections of the same type into one section. We may have multiple .o files, and those .o files will be linked later on. So relocation is a procedure in which such relocatable object programs are created which can be merged by the linker later on. Anyhow, the assembler basically converts the assembly language to machine dependent code, and each of the object file which is created contains a symbol table, and that symbol table contains name, type and relative addresses of global variables, The first thing, let me repeat it again. The name, type and relative addresses of global variable. The second thing is the name and relative addresses of functions defined within the file. And the third important thing is only the names of functions which are not defined in that file. For example, if your C program is using the printf function and its definition is not of course there in the hello.c file, so this symbol table contains the name of those functions which will be relocated later on to a particular address. Anyhow, the last phase is the linker phase. The linker actually links the code of the printf inside the hello.o to make it an a.out file. Now remember, this printf.o code resides in a file printf.o. And this printf.o is part of the standard C library. And in our machine, you can check out the standard C library's location is usr lib x86 underscore 64 hyphen linux gnu, and in that directory libc.so or maybe libc.a. This is the static version of the standard C library and this is the dynamic version, shared object of the standard C library. So anyway, so finally after the completion of these four phases, we will get a file a.out. If we want to perform all these tasks in one step, we can simply write gcc hello.c. This command will take this source file and generate the file a.out directly. If you want to perform the steps one by one, you can use 1, 2, 3 and 4. These four steps separately for pre-processing, compiling, assembling and linking. You can also use this single command which will temporarily save all the files which it will generate during the creation of the final executable a.out. So let's move on to our Linux machine and try doing it. Sorry for giving the wrong password. Okay, so here we are. Our current working directory is in my home directory Lec07. I have a file hello.c over here. Let me cat it first. So this is a very basic file hello.c. If I do gcc hello.c, it will generate a file a.out, and if I run a.out, it will of course give me the expected output. Now if I want to perform the steps one by one, I can do that, but let me use the -safe -temps option to gcc, saying it to temporarily generate all the files for pre-processing, compiling, assembling and linking. So this is a file which contains the pre-processed code. This is the file which contains the assembly code. This is the file which contains the object code, which is also known as the relocatable file. And this is our final executable. Remember gentlemen, this is also the machine dependent file. This is also the machine dependent file. But this cannot be executed .o file cannot be executed because it still contains some symbols which are not resolved, like printf. And this a.out contains the definition of the printf function as well, if it is statically linked, or if it is dynamically linked, it will be linked during load time. Okay, gentlemen, here I will like to tell you the formats of these object files which are created by the compiler. So this is what I have done it so that we can save a bit of time. So the compilers generate 4 different types of object files. Rather, I should say 3, 1, 2, and 3. So core file doesn't fall in this category exactly. The executable object file that contains binary code and data in the form that can be copied directly into memory and executed. So this is an object file that can be executed. The second is the relocatable object file. These are normally something .o files, and these are normally called a.out files. These are the actual executables, whereas these are non-linked object files, also called relocatable object files. These relocatable object files contain binary code and data in the form that can be combined with other relocatable object files at compile time to create an executable file. So multiple .o files are combined to make a final executable. As we have seen in the previous example, our object file hello.o is combined with the printf.o to make final a.out file. The third one is the shared object file. We will talk about the shared objects later sometime. It is a special type of relocatable object file that can be loaded into memory and linked dynamically at either load or runtime. Normally, the DLL version of the Windows file. Finally, the core file. Gentlemen, this is a disk file containing an image of the process memory at the time of termination. At times, you might have seen that your code has generated a runtime error like division by zero or segmentation violation. So they terminate by generating a file. They terminate by generating a file so that you can load that core file in your debugger to carry out the postmortem of the process and find out the reasons what has happened to your process once it died. Gentlemen, just in case if your core file is not generated, which is the default behavior of Ubuntu, you can give this command on the terminal: ulimit -c unlimited. We'll see it sometime. Anyway, so as far as the formats of object files are concerned, these are the 4 formats which I would like to discuss. This a.out is actually the executable format used by initial versions of Unix. By initial versions of Unix. And to date, the executables are still referred to as a.out. That's why once we do GCC, we by default get a file whose name is a.out. Of course, you can change the name of that file as well. Later on, in System 5 Release 3 Unix, the format of object files to change to COF, Common Object File Format. Common Object File Format. It was used in System 5 Release 3 and later on in System 5 Release 4 and in Linux these days, the format that is used is the ELF. And PE is the format, Portable Executable Format. This was the format used by Windows, particularly Windows NT. So I will be more interested in this executable and linkable format. So this is the format in which your actual a.out or the final executable on the Linux machines are created. So let me briefly touch upon the various components of an executable and linkable file format. I have prepared snapshot of that as well. So this is the actual view, pictorial view of a program on disk. Once you create a program after following the 4 phases of compilation, so this is what is actually created on the disk. Soon I will show you on the system as well. But right now remember there are 3 main things. The first is the ELF header. The ELF header basically that contains information that allows a linker or loader to parse and interpret the object file. It contains information which are used to parse the object file, to mix different object files, or to load an executable file into the memory. Then the second main portion is the program header table, and we have the section header table as well. These data, let me change color. This portion actually contains the machine code. The actual code which you have written, which is compiled and converted into machine language. This .ro data is basically the read-only data, like the string literals or constants that you have declared in your code. This data is actually the initialized global and static variables. Remember, this data is the initialized data. This is the initialized data, whereas this BSS is the uninitialized data. BSS is basically IBM 704 assembly instruction used way old back. Is the abbreviation or acronym of the block storage start. BSS is the abbreviation of block storage start. It is IBM 704 assembly instruction. Actually, this is the uninitialized, it contains uninitialized global variable. Suppose if you have a global variable int ARR sub 1000, so, and assuming that integer is of 4 bytes, that doesn't mean that this portion will occupy 4000 bytes. So to me, BSS is basically for saving the space. It would be better if we can call it better save space, BSS. Anyway, this sim tab is the symbol table containing information about functions and global variables that are defined and referenced in a program. These two portions, dot relative text and relative data, they are the relocation information of text and data that need to be modified when a linker combines this object file with other. In case if this is a final executable file, these two sections will not be there. These sections will only be there if this is an object file. Finally, this .debug, it contains debugging symbol, and this will be there only and only if you use -G option with the GCC to tell or instruct the GCC to add the debugging symbol in the final executable. This .line portion is also for the debugging. It basically is used to map the source line numbers and the machine code instruction in the .text section, and this will also be there if you have the -G option compilation. You have used -G option for compilation. So this gives you the mapping between the source instruction and the machine level language instruction, so that you can get the exact error of the source line generated by the machine code. Okay, so gentlemen, this was the pictorial view of a program on disk, and if you want to view the contents of this file, you can use the program readelf. So let me try it on my machine. So we have an executable file a.out. Let me do read elf a.out. There are a lot of plethora of options that we can give with read elf. If I give the -a option, it will give me all possible information. And if I just want to suppose see a particular portion of this file, let's suppose I just want to see the elf header, so I can give the -h option. So you see, so this read elf -h a.out, it tells you information about the elf, tells you about the magic number. This is the magic number, which tells you something about important information about the file. And if you want to know what this magic number is, we can do man elf. So this is the man page of elf. You can scroll down and you can find out what these magic numbers actually stands for. There are plethora of information in the man page of the elf file, but anyway, it tells you about the class, the data, whether it's two's complement or one's complement, the machine is little endian or big endian, the application binary interface it is using, Unix System 5, then the size of this header is of 64 bytes, the number of program headers are 9, the number of section headers are 30, and the size of section headers and blah blah blah. So all this information ELF header contains, which is read by your loader so that it can read this entire file from the disk and bring it inside the memory later on. Similarly, you can use -h option you have seen to view the ELF header. If you want to view the program headers, you can use the -l option. If you want to view the section headers, you can use the -s option. And if you just want to see the symbol table, you can use the -s option. This is for symbol table. Let's check the symbol table of our file. Oops. Let me shrink it a little bit so that we can see it in the file. So this is the sim tab. It has having 65 entries. You can see this symbol over here, put s. This is a symbol which we have used in our code, that is the printf code, which is converted to put s. If you have used a lot of other symbols as well and variables, you can find those in the symbol table. Their relative addresses, their type, their bind time values, and blah blah blah. So there are a lot of plethora of information that you can find out, and that may be of quite usage to you. Anyway, so dear students, once we have created a program file on disk, now the next task is how we can load this into the memory and make it a program. So loading a program into memory. So program loading is basically copying a program, an executable object file, from hard disk to the main memory in order to make it a process. So that it can run on the processor. And once it is loaded, it is placed inside the red queue and it waits for its turn to be executed by the CPU. But we say whenever a program is loaded inside the memory, it is known as a process. So what is a process? You must all have read the basic definition of a process is that a process is an instance of a program running on a computer. Let me write it for you. Instance of a program running on a computer. Remember, gentlemen, one program may be used to construct many processes. For example, you can have many instances of a browser running on your system at a time. So we can say that one program can be used to construct many processes. And similarly, we can say that many processes may be running the same program as well. So anyway, so there is one very important component that is used by the operating system kernel to control the process, and that is known as process control block. For Linux kernel developer, it is known as the task struct structure. Task struct. So this is a structure which contains plethora of information, lot of other structures which are used by the operating system kernel to manage a process. But the information which a process control block have can be divided into three main categories. One is the process identification. The process identification can contain the ID of the process, normally called the PID. It can contain the parent ID of that process, normally called the PPID. Can contain the session ID for that process. It contains the UID of that process. It may contain the EUID of that process. It may contain the saved set user ID of that process, and so on. So there are a lot of process identification. Then we have the process state information. All the CPU registers, the values or the contents of the CPU registers determine the state of that process. The contents of program counter tells you which is the actual line of code which is going to be executed next. The flags contains information about various operations. Similarly, there are registers containing addresses of the code section and the data section and the extra segment as well. There are registers which are containing the addresses of the stack, the base of the stack, the top of the stack, and so on. Finally is the process control information. When is the process created, how much resources it has opened, how many files it has opened, how many child processes it has created, what are the different memory constructs it has used so far, so on and so forth. So all these information are there in the process control block, and we say the task struct as well. So this is the theory of our process in Linux. We will like to see it. So this is the pictorial view of a process in Linux. This is how a process looks like in Linux. So in the very bottom of this, let me take this color. So this is the place. This is the place which is unused. From address 0, let me use this. From address 00000. So from address 0 to 0x08048000, we have the unused portion, and after that we have the text section. This is the place where you have the read-only code of your program, which we call .text in a realf format. Here we have the initialized data. Here we have the uninitialized data, which we call the BSS over there. And then we have the heap, which grows upward. Heap grows upward. And this BRK shows the break, the top of the heap. This heap is created at runtime and it grows at runtime. Created at runtime. eText points to the top of the text section, eData points to the top of the initialized data, and end points to the top of uninitialized data and the start of the heap. And BRK points to the top of the heap pointer where the heap has grown till jet. And if we come up from the top to bottom now, and this is the topmost highest address, high address. Almost about 1/4 portion of our virtual address space is occupied by the kernel over here. So this is the place which is occupied by the kernel. It is not visible to the user code, and our user code starts from here below. So this is the maximum address which a user can access At the top we have the command line arguments and environment variables. Below that we have the user stack and mainly the stack of the main function, sorry, and then every function has its frame inside this is its user stack. The top of the stack is pointed by this register, the stack pointer, and the heap grows upward and the stack grows downward, and in between them we have again a reserved area to contain the shared memory mappings and the shared libraries, and these are what I talked about previously as well, the DLLs. So gentlemen, this is the overall view, pictorial view of a process. You must all have the picture of a process in your mind whenever you are talking about processes, that they have the reserved area and the at the bottom, then they have the text section over here, then they have the initialized data, uninitialized data, then heap grows upward, and at the top we have command line arguments, environment variables, and then we have stack which grows downward. And this is the top address which you can use over here, and from here to here we have the kernel space for virtual memory of this process. Right, gentlemen, so this is also, we are done with this. So let me now move to the Linux again. Right, gentlemen, now the shell gives you a lot of facilities. One of the facilities is running the processes, executing them in the foreground as well in the background. So you can run a process in the foreground as well as you can run a process in the background. For example, ls, so this is a process which is running in the background, in the foreground. It is holding the terminal. Let's suppose I say sleep, sorry, for 5 seconds. So we are sleeping for 5 seconds. It is holding the terminal. After 5 seconds it will terminate, and the control will come back to the user. So a foreground process run on the screen in foreground. It may hold the visual display unit, it may hold the keyboard, and it may require both. For example, vim abc. Now vim is a program which is running in the foreground and it is holding the keyboard. So whatever I type over here, and it is holding the screen as well at the same time. Similarly, if I run a program, let's suppose less hello.c, so less is also running in the foreground. It is holding the video as well as the keyboard. On the contrary, a background process is a process that run behind the screen in the background, and usually do not need either the VDU, visual display unit, or the keyboard. For example, an audio player playing an audio song may not require user I/O for about 5 minutes or so till the time the song runs. Similarly, a find program which is searching a file from a huge file system may take a few seconds or maybe a minute or so. Such programs should be run in the background so that the terminal is available to us for execution of other commands. In GUI, gentlemen, we simply minimize an application and run other applications. But how we can achieve this on the terminal? So what we are going to learn is how we can run jobs in the foreground and in the background, and how we can switch between them. So let me run a program. Let me run a very simple program for you. Sleep 5000. So I have run this program. It is running in the foreground. Now the terminal is not with me. What can I do? I can send it to the background. To send a foreground process to the background, you can press the Ctrl plus Z character. Once I have pressed the Ctrl plus Z character, you see the sleep process is stopped. The sleep process is stopped. You can view that by using the jobs command. The jobs command actually tells you what all processes are running or not running in the background. And this time jobs command has told me that there is a program sleep which is in the background and it has been stopped. If I want to run this program, I can give it a command like bg. So if I give a bg command and then I give a jobs command, it tells me that the process has started running. Let me repeat this procedure again. Once I run a program in the foreground and later I feel like running it in the background, I suspend that program by pressing the Ctrl plus Z character. That process is stopped and I can confirm that using the jobs command, and then I need to run it in the background, so I use bg. If there is only one job that is in the background, I just give the bg command. If there are more than one job, then I want to run a background job, a specific background job, I give a number with that. So let me repeat it again. So let me kill this process. Okay, so let me say sleep 5000. Now this is running in the background. I press Ctrl plus Z. It has stopped. I give bg and I give the number of the job ID of this process, and I say jobs now. So you see it is running in the background now. Okay, let me run another job now. If I'm going to run this job in the background, I'm going to paste an ampersand sign at the end. Now if I press enter, this job will run in the background. You see these both jobs are running in the background. If I want to bring a background job in the foreground, I can use the fg command, and I say fg and I give the, let's suppose, the job ID. Let's suppose the job ID of 2. I press enter. You see the job ID of 2 has been brought in the foreground. Let me again suspend it. Jobs. You see this is stopped. Let me run it. bg2 jobs. So it is running. So gentlemen, jobs, fg and bg. These are the 3 commands. All 3 are built in that are used to manage the jobs, run the jobs in the foreground, in the background. To suspend a job, you use Ctrl plus Z character. To run a program in the background from the very beginning, you use the ampersand character. So please do practice executing jobs in the background as well as in the foreground. We move on to another very famous command related to processes, that is the PS command. PS stands for process status. So PS command reports a snapshot of the current process. So there are a plethora of information on this. PS is a very old command, so you can find variations of this command on different machines. You give a lot of options to PS. In case of Unix, the option must be preceded by a dash. In case of a BSD Unix, they must not be used with a dash. And if you are using the GNU, then you must proceed 2 dashes. So you can read all this information. There are a lot of examples as well over here. Make it your habit to see what your processes are doing and in which state they are running. what all resources they are holding using the ps command. If you simply type ps and press enter, it shows you 4 columns. The first column is the PID of the processes which are running right now. The second column is the terminal to which they are attached to. The third is the time since the process have run. And the last is the command. You can see these are the 2 sleep commands which are running in the background, and this is the shell, and this is the recent command which we have used. Similarly, you can use ps-a command to use all processes running on all the terminals. If on this terminal I'm running a command, for example, another sleep with 2500 in the background, of course, and over here I use simple ps, I will not get that sleep. But if I use it with -a option, I will get that third sleep as well. So it is controlled by PTS12. This is the PTS12. On PTS12 I have run another sleep command. So -a option is used to show all the commands running on other terminals as well, and if you don't use -a, it will show you the commands running on the current terminal only. Similarly, there is another very good option, that is ps-u. -u is basically used to display 11 columns of information for each process. Let's talk about this process which we have just run. The last column is the name of the command. The first column is the user who has run this process or command. The second column is the PID. The third column is the percentage of CPU it is using or recently used, which is nothing right now. This is the memory, and of course it is not using much of the memory. This is the virtual memory size in kilobytes. This is the resident set size, non-swapped physical memory that the process has used. This is the terminal to which it is associated to, and this is the stat or the status of this process. I will talk about this from man page. This is the start time of this process. This is the time again. Let me tell you what this SS or SS plus or S or R plus stands for. Right, for the time being, gentlemen, remember the different states a process can be in R, S, D, T or Z. If a process is running, you will find an R written over here. You can see this R. And if a process is sleeping for some event, then you will see an S over here. If it is in an uninterruptible sleep, you will find a D over here. If it is being traced by a debugger, you will find a T over here. And if it has become a zombie, you will find a Z over here. We will see what zombies are later on. But right now, let me open the man page of PS, and then let me search for process state codes. Process state codes, PROCESS. Okay, so these are the process state codes, DRSTWXZ. These are the codes that can be used, which I just talked about, and along with these codes you may find these additional symbols with them. As you have seen the plus sign, the plus sign shows that is a foreground process, and you might have seen the S sign as well, which shows that it is a session leader. Let me show you again. This plus sign, this means it's a foreground process. All these processes are foreground. Bash shell, they are all foreground processes. You don't see a plus sign over here with the sleep. This is in the background. So plus is for foreground and no plus is for background, and this S is for session leader. Of course, every terminal is a session leader. Anyway, gentlemen, so this was a -u option. Then you can have -l option as well. -l option displays about 14 different columns in the output. The first F is the flag. This indicates whether the process is a user or a kernel process, and why it has stopped or went to sleep. Here it is giving us no information. Then we have the state, as we have discussed before. This is the UID, user ID, and of the owner who has run this program, bash program. My UID, Arif's UID is 1000. This is the PID of this process. This is the parent ID of the process, and this C shows the CPU usage, which is very minimal, almost nothing. This is the priority value of a process. Remember, gentlemen, a higher priority number means low priority in Unix. So we'll talk about priorities sometime later. This is the nice value. This value can range from minus 20 to plus 19. We will talk about nice value as well later sometime. These are the addresses of process in memory on disk in case if it is swapped out. So it is just a dash over here. And SZ is the size of the process in blocks. This WChan is the wait channel. You will find a dash for a running process, and you will find a the event for which the process is actually waiting. So these sleep processes are waiting for this event, a restart event, and this bash is also in a wait state. You may find a star over here sometimes somewhere, because in case if this is a thread, you will find a star over here, because PS doesn't work well on threads. This is the terminal, and this is of course the time. So gentlemen, to cut it short, PS is a very powerful command. You must make it your habit to use PS occasionally. And finally, the top command. Top is an interactive command. This is continuously refreshing it and giving you again a plethora of information about various processes which are running. It shows you real-time information, gentlemen, and by default it refreshes its output every 3 seconds. This is the summary area of the top command. You can see 1, 2, 3, 4, 5. There are 5 lines which are shown at the top of the top command output. The first line, let me highlight, since it is refreshed again and again, so that's why I couldn't highlight for much time. So anyway, the first line displays you the current time, the time since last boot, the total number of users. Right now there are 5 users, 5 different users, 4 Arif and 1 root. And this is finally the load average of the system over the last 1 minute, 5 minutes and 15 minutes. The second line, gentlemen, this shows you the total number of processes, 165, the running processes at a time. Since I have multiple cores, so we have multiple number of processes running at a time, 2 and 3. These are the processes which are sleeping, waiting for the turn. These are the stop processes, and these are the zombie processes. We will talk about zombie processes later on. The third line shows you the CPU usage. The fourth line shows you the memory information, physical memory, and the fifth line is the virtual memory usage, total, used, free and cached. And finally, this is a space over here where you can use your own inputs. For example, H for help. I have just pressed H, and you have seen that I have moved on to the help screen. A lot of commands that you can give to the top. For example, if you press N, I have just pressed N, the top will ask you the number of processes to be displayed. I press 5. So now it is displaying just 5 processes, 1, 2, 3, 4, 5. Let me press N again, and let me just give 0 and press enter. So it is unlimited number of processes over here. If I want to display processes of a particular user, I just press U. So which user, blank for all. I just say that I want to see processes of root process only. So you can see only root user processes are being displayed. Let me say Arif. So processes of Arif are over there. Similarly, if you press S over here, it asks you for the time, after how much time it should refresh. I say refresh it after 1 second, suppose. So now you see it will be refreshed after 1 second. So gentlemen, the upper information is about the whole system, and the information shown in the lower pane is about a particular process, the PID, the user, the priority, the nice value, the virtual memory status, resident set size, shared memory, the state, the percentage CPU, percentage memory, time, and command, and so on. So there are a plethora of information the top gives you. Okay, so few more commands, gentlemen, before we say goodbye to each other. Free. Free basically is a command that is used to display the amount of free and used memory in the system. For use free, this gives you the total memory, the memory used as buffer, the memory used as the swap space, the total used, free, shared, and buffered and cache. So this information is of course available with the top command as well and with the free command as well. And then is the vmstat. Vmstat is a command that is used to display information about the virtual memory. These two columns are related to process. The first R is regarding the number of runnable processes. This B is about the number of processes in uninterruptible sleep. Then we have this information from here to here regarding the memory. Swap D is the amount of virtual memory, and free is the amount of free memory, and this column shows you the amount of memory used as buffer, and this portion shows you amount of memory used as cache. And from here to here, two columns for the swap, and this SI shows you the amount of memory swapped in from disk, while this SO shows you the amount of memory swapped out to disk in terms of block. Over here we have the IO, two columns for the IO, BI and BO, blocks received from the block device and blocks sent out onto the block device. This is again the information about the system. In and CS. This in 203 that tells you the number of interrupts per second, including the clock interrupt. And this CS, which we will be talking about in scheduling as well, this shows you the number of context switches per second. So we are having 502 context switches per second. And finally, this is the information about the CPU, which we have seen in the top as well. And the first US, let me tell you about this. This is the time running for the user processes, and this SY is the CPU percentage time running for the kernel processes. This ID is the time spent by the CPU in the idle state, and W is the times waiting for the IO completion, and this ST is the time stolen from this virtual machine by the hypervisor. So gentlemen, there are plethora of information which are there in the free as well as the vmstat command. Finally, there is another very simple command, uptime. Uptime is a command that you can use to find out how long the system has been up and running. So this is the current time, it's almost 8 o'clock, the dinner time, and this is the time the system is up and running since last almost about 18 hours 32 minutes. There are 5 users who are currently logged in, and the load average again, the load average since last 1 minute, 5 minutes, and 15 minutes. Finally gentlemen, another command, this was just a prompt that sleep 1000 has expired. The watch. Watch is another utility normally used by programmers. Watch is used to execute a program periodically, showing the output full screen. For example, if I want to say free, so this tells you the memory, physical memory status on your machine. If you want to continuously watch it, watch free. So you pass a command name to the watch program, and the watch program runs this command and refreshes it every 2 seconds. You see, every 2 seconds the free is being refreshed over here. So gentlemen, that is all about for today. Today we have talked about processes. We have seen processes. Let me come up to this screen so that I can just briefly review what we have done. I don't want to run Siri. So we started with the C compilation process. We have seen the stages. I will recommend you very strongly that you should have very clear idea what pre-processing, compiling, assembling and linking does, and you should do it on the terminal. Then we have seen the types of object files: executable object files, relocatable object files, shared object files and the core files. And we have talked about the 4 different formats of object files, and in those 4 different formats we have talked about the ELF format in particular, and this was a pictorial view of the ELF format file. And you should have this in mind always, that it contains the ELF header, program header table, and in the bottom section header table, and in between it contains a lot of information which are used to build a process from program. And read ELF is the shell command that we can use to dig out the information stored inside the program on disk. And we have seen that this program is loaded inside the memory to make it a process, and a process is basically an instance of a program running on a computer. And the very important data structure for every process is the process control block, which contains plethora of information that is used by the OS kernel to manage and execute processes. And this is the pictorial view of our process, and you should remember that the addresses grow from bottom to upward, and at the very top we have the kernel virtual memory, which is not visible to the user code, and in the bottom we have again the unused portion, which is at which place some startup routines are placed by the GCC compiler. And finally we have used commands like let me open up another view. Okay, let me use that this time. So we have seen that how we can run processes in the foreground, background. We have used the jobs command for this purpose, the FG and the BG command. These 3 are the built-in commands. We have used Control plus Z to suspend a foreground process, and later on we have used the PS command to process status command that displays information about a lot of processes, and we have used the -U as well as the -L option to display 11 and 14 columns information respectively. We have used the top command, which is an interactive command, shows you plethora of information regarding the system as well as on all the running processes. We have seen free, which displays amount of free and used memory in the system. We have used vmstat as well, that displays virtual memory statistics. Finally we have seen uptime, that show how the system is up and running, and we have used watch as well, that is used to execute a program repeatedly after every 2 seconds. So gentlemen, I will strongly recommend that you should practice these commands. You should go through the main page of these commands so that you can learn a lot about these. Okay gentlemen, I wish you all the best. Hopefully next time I will be talking about something about process scheduling, and we will see what are the tools and the commands available to us by Linux, which we can use to dig out information regarding the process scheduling states. I hope the lecture was informative, and I wish you all the best for your future endeavors. Good luck and happy learning. जहाँ का सबात है तुम ही से ऐ मुजाहिदो, जहाँ का सबात है।